Good morning, everybody. We are going to start a new lecture in electromagnetics, and today we will somehow start with transmission lines. Now, first we will talk what transmission line is characterized by. Then I would like to focus on the coaxial cable, which is one of the oldest yet still very much used transmission lines. It's possibly also one of the simplest transmission lines because we can use some knowledge that we have already developed within this course. So I will start with that. But anyway, later, let's say at 9 o'clock, we will stop lecturing and make some decisions on examinations, like when and so on. So again, now let us start with transmission line. What a transmission line is, that's a device that is created in order to support transmission of power or energy or information. That's important that we understand that this is both the same from the standpoint of transmission lines. Now, we have learned that a transmission line is something through which the information or energy is propagating. That means it takes some time to reach one end from the other end. This time delay is one of the possibilities to watch for. Then there is another parameter that is very important, and this is wavelength of a wave at a certain frequency. Now, how this is related to propagation delay? We mostly, as engineers, if we can, work in something which is called harmonic wave. And harmonic waves are waves that never exist in reality, because a harmonic wave is a wave which had the harmonic behavior already before the start of the universe and would have this behavior also after any end of the universe, if there was any. So this is important that we have a fiction, which is the harmonic state, but we like it very much because it's very simple. Now, when time changes are very slow when compared to the frequency or period of our signals, the harmonic state, the harmonic signal, is quite a good approximation. And within this, all our rules like resonance, capacitance, impedances, admittances work very well. So we as engineers are very tending to use harmonic state. Now, if we have a transmission line, and what happens in reality, there is a propagation delay when the wave is propagating through the line, we convert this to a phase shift. And our measure for that in harmonic state, after transforming the reality by a Fourier transform to a universe of frequencies, is something which we call phase shift, and this is very connected to a property that is called wavelength. So we would like to know for any transmission line the wavelength of the wave propagating through that line at a certain frequency, because all those lines somehow relate frequency to wavelength. Even a free space has a relation between frequency and wavelength, and in that space it is inversely proportional. The higher the frequency, the shorter the wavelength. Now, this is one of the properties we should also find out a property which is called characteristic impedance, but characteristic impedance is something we should first talk about to understand that. So I will start with a coaxial cable and its behavior when transmitting power and information, and we will derive what the characteristic impedance is and what the meaning of that impedance is, and then we will possibly be able to have that also for other lines. So let us start with a coaxial cable. First, how does that look like? So a coaxial cable is a system of two conductors. One of them is inside, so we call it inner conductor. The other is outside, so let's call it an outer conductor. And the line, of course, is of some length. Now, in a coaxial structure, both cylinders, the inner conductor and the outer conductor, do have the same center. So we have two radii, let's call it A and B, and it's important to keep both cylinders insulated one from the other, so that we have some dielectrics inside in the cross-section of that transmission line. Now, we should investigate how a wave which gets inside the coaxial cable should behave. And once investigating a wave, we would have to resort to a wave equation. Just a short remark. Well, in fact, a coaxial cable has been used for more than 100 years. As far as I remember, the first publication that has analyzed most of the equations we will be deriving today has been published in Bell Labs journal in 19126, I think. And for many years, this analysis of a coaxial cable was the only available. Now, that analysis did not take into account losses, and a full description of a lossy cable has been done by Ben Wade from National Institute of Standards and Technology in 1996 only. And that still is not a full description because it considers the outer conductor as infinite. So then, for example, we have our numerical system which handles a real coaxial cable with losses, but the results are not so fancy to be compressed into a few equations, so we have not been publishing that. So still a coaxial cable which is used more than 100 years is not fully analytically solved to have good representation according to losses and dispersion. But anyway, a simplified expressions, those that have been published by Shelkunov at the early stage of the 20th century, would be presented now, and they are good enough for technology. So first, we should investigate a wave that is propagating along the coaxial cable. So the wave should satisfy a wave equation. We already know that. For example, we would have the Laplace operator imposed on electric field strength, which, yes, is a vector and phasor, plus k squared E vector phasor is 0. So we have this equation. We already had it some time before. Now, with this equation, we have a problem. It is an equation covering harmonic field, which is nice. We have ruled out time. But still we have three variables as to space. And that's too much to be solved conveniently, at least for analytic solution, that's too much. So let's try to get this kind of solution a little bit simpler. And the first thing we can do is that we decide not to solve general field contributions, general field arrangement. We are first going to get a solution which is a solution for a propagating wave. Well, if we find it, we are happy, we have the solution for what we need. If we do not find that, well, we do not care for other solutions. We need a propagating wave, and a wave propagating along a structure should have some phase propagation constant. Let's call it beta. Now, by telling that we have a wave propagating along this direction, let's call it Z, that wave should have some dependence of electric field strength or magnetic field flux density or any measurable quantity, which should be a dependence relevant to a propagating wave. Okay, then it must hold that with respect to variable Z. The electric field strength phasor must hold this kind of relation. It should be some E0, that is the quantity at the beginning of the z-axis, times E raised to minus j beta z. You know this behavior, that's the same with a plane wave. So this describes a wave that is propagating in the z direction. We are searching for this solution only. If there is another solution, it does not fix an electromagnetic wave, so we are not interested in it now. So let us try to input this, substitute this to the equation. Well, we have a nabla operator, which is a sum of partial derivatives against x, y, and z. And we now split it into two parts. Let's call it this way. We have a nabla operator, which depends on x, y, and z. And now we split it into two parts. The first part is nabla in cross-section. It could depend on x or y or radius and angle, whatever it depends on. It is completed by a second component, which is the nabla along the xz. But this is only one variable, so let's forget about this notation and put it straight. It's the second derivative against that. Having this in our minds, we can rewrite the equation. So let's first tell that we have this derivative against z, and we know that the function of E is written just here. We know how the wave behaves as to the z coordinate. So in applying this nabla here, we can directly express the second derivative of E against z. Just let's make it for convenience here in green color. So if we apply a second derivative against z over here, so if we derive this against z, we would get, it's an exponential after all, so we make the first derivative, that as we multiply by minus j beta, and then we apply the second derivative, and we again multiply minus j beta, which means that that the second derivative of this must be Ez itself times j beta squared, and j times j is minus, so we would finally arrive to a conclusion that we can carry out this derivative, and that would be minus beta squared. So we have a conclusion that the second derivative of E against Z would be equivalent to E times or minus beta squared E. And with this knowledge, we can rewrite this black equation again. Now what we get is we have the remaining portion of nabla operator, the transversal operator, the cross-section one, applied on E, plus k squared minus beta squared E, and this must be 0, that's the original equation. So we have, after some manipulations, changed the original equation, which had 3 unknowns, x, y, z, for example, into a simpler equation, which has only 2 variables in the direction of cross-section, but we have ruled out the dependence in the z direction, because we already know it. If there was a propagating wave, it must behave like a propagating wave. That is, the z dependence must be e raised to minus j beta z. And this is an important equation. I will rewrite it on the other white paper sheet. So we have a new form of equation, and that's the equation just written here. Now we can easily see that this equation is very similar to the original wave equation, just we replaced k squared by an expression k squared minus beta squared, and we have had a nabla operator in 3 dimensions, and we have now only in 2 dimensions. But that's a very similar look of the equation. And now we can try to solve for specific cases. For example, what happened if k is equivalent to beta? Now, if this was the true, let's try whether that makes any sense in the terms of electromagnetic field. So let's say that k is equivalent to beta. Let's make the proposal. This is the situation. What would happen then? Well, first we would have this term vanished. So now our new equation is a bit simpler. It looks like it's much simpler. first, it looks simpler. There is less terms in this equation. Second, it's a special type of equation which we have already seen in electrostatics. And this equation has been called a Laplace equation. And we know that there is a solution to that equation. And we know that solution for a coaxial cable, in fact. We already know that. So what we can tell now after having this solution or this simplification, well, we can tell there are possibly several ways of propagation for an electromagnetic wave in a coaxial cable. And now we have figured one of them, which seems to be the simplest one. And this way happens in a special manner. There is, of course, the dependence on the z direction, which is the dependence that is proper for any electromagnetic wave. But if we count the dependence of electric or magnetic field in the direction of cross-section, we would have there the solution that was already derived in electrostatics. Just let us remember that solution and put it down. So if we have a coaxial cable, I will draw a black one. So as to cross-section, there is the radius A and the outer conductor with radius B. And this is dielectrics. And now we know that the electric field strength has the character of arrows going from the inner conductor to the outer conductor. So I will draw, say, 5 of those flux lines. So this is E. And this E, which is radial, is given by, you remember from electrostatics, the charge density per meter on the inner conductor divided by 2 pi epsilon r. Well, epsilon is the permittivity of the material inside. Now, we have also magnetic field, and that should have the character of circles that are concentric with those two metallic conductors. So I will draw but 2 of those lines, and all that should have been concentric circles. And as to H, the magnetic field has only azimuthal direction, H phi, and it is given by I, which I is the current flowing on the central conductor, divided by 2 pi r. Just note that electric and magnetic field are in any point of the cross-section perpendicular, which means that if we construct the Poynting's vector, we can directly multiply the magnitudes of those two vectors. So at any point inside the coaxial cable, we would have the Poynting vector of S that would be pointing into the board, and we can get it just by multiply ER by H phi, which would be now we have still too much unknowns. There is some charge density, some current, which is a lot of things, and we would possibly have to think over a little bit what happens in the cable. Now let's do that, and I will have a special consideration about that, which would relate electric and magnetic field inside the cable. I mean, we should have written, or we could have written also the same equation for magnetic field intensity, and it would result in the same expression, just having H here instead of E. We would have to find some relation between the current and voltage on the cable. So let us try to find whether there is any relation for this wave, which could be measured from outside by simple apparatuses like a voltmeter and ampere meter. So if we would have the cable, it would be very long, and at the input we would measure by an ampere meter the current and measure by a voltmeter the voltage in between the inner conductor and the outer conductor. We could possibly have some meaningful relation between those two quantities. This would be quite easily called an impedance. So if we have an impedance, we would have something we can measure by a voltmeter and ampere meter, and dividing those numbers. Then let's try to derive whether there is such a quantity and could be derived from the electric and magnetic fields. We already know the expressions for those fields, so now we should start somehow to get the idea of the characteristic impedance. So we have the inner conductor and the outer conductor, and let us start with an inner conductor that bears a current flowing inside the paper, and the current is just I. Now we know the magnetic field intensity, which is created by this current around the conductor, and it could be easily expressed by this equation. So at any point over here inside the dielectrics, we know already the magnetic field intensity. And now we can do a small trick. We called that something propagating through the cable a wave. Well, if this is a wave, it must keep an important relation. We already know the free space or the dielectric impedance, which is given as a ratio between two perpendicular components, E and H, belonging to the same wave. We have two perpendicular components belonging to the same wave. So we are able to find out the electric field strength out of the magnetic field intensity, and then therefore out of the current flowing within the coaxial cable. Let's do that. So now we will have an important relation, and that is introducing this quantity, which is, by the way, given that by the properties of the dielectrics of the cable as a square root of a ratio between mu and epsilon, permeability and permittivity, and then we could possibly use that. So we have this relation for H. Now we can derive the relation for E. We know that the impedance times magnetic field intensity gives the electric field strength. So if we multiply this, we will achieve electric field strength, which is radial, as a function of radius would be we first rewrite the magnetic field component I over 2 pi r, and then we should multiply that by the free space or wave impedance, and that would be a square root of mu over epsilon. Now we have the value of the electric field strength, and just rewrite that from the second picture. It has this direction. So insofar we have the current flowing into the cable, and we know the electric field strength as a function of radius within the cable. What we can do now is to find out the voltage, because the voltage could be found by integrating electric field strength from one conductor to the other conductor. The simplest way to do that is to integrate over a path which is exactly running radially. So this will be the integration path. Now we can put down that we have the voltage equivalent to an integral from A, this is the radius of the inner conductor, see the other picture, to B, which is the radius of the outer conductor, and the integrand would be I over 2 pi r square root of mu over epsilon, and we will integrate dr. And this is a very simple integral, as we can find out constants as to r, which is I 2 pi mu epsilon. So after shifting all those out of the integral, we have an integral from the function 1 over r dr, which is a simple textbook integral, a natural logarithm of r. And therefore the result of this integration would be I over 2 pi square root of mu over epsilon logarithm of b over a. And now what remains to get the impedance? We have voltage, we have here current, and we may now derive the relation between voltage and current that belongs to a wave propagating through a coaxial cable. Now let's do that. So what the relation would be? Well, the impedance I put here characteristic impedance of that cable, which is a ratio between voltage and current, would be so it is this expression divided by current. So we can write it as a square root of mu over epsilon divided by 2 pi logarithm of b over a. Although this is a simple equation, it is in most times simplified even a bit more. We know that the mu0, the free space permeability, is equivalent to four pi times 10 raised to minus 7th order. So if we get those pi's from here, and this impedance already is 120 pi ohms for a free space. Now I will rewrite this a little bit. So for free space it holds, if that something is non-magnetic, it is 120 pi ohms divided by a square root of relative permittivity. This is another expression for lossless media. Now if we introduce this here, we have the final equation, which is very important to all radio frequency engineers, and this is 60 over a square root of relative permittivity times logarithm A divided by B. And this is the equation that can give you the characteristic impedance of a coaxial cable. So, as a result, we know that for a wave propagating through a coaxial cable, there is a given ratio between voltage and current. This ratio is called characteristic impedance and can be calculated with this simple equation. Now, this is something that is very important to radio frequency engineering, and I will tell you a very nice story about that, which is so old that I can tell it now easily. Well, some possibly 30 years ago, I have been a freshman working with my little bit older colleague, and at that time we have been in the same room, and suddenly he has got a phone call. There was a company that has been producing coaxial cable conductors and coaxial cable components like connectors, and they have been producing that because